Good afternoon. Welcome back to Codex. Many, but not all, of our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today, we're very happy to have Simone Ruetz to be the first speaker in this series. Simone is currently a graduate student at the University of Innsbruck, graduating in September of this year. His research, advised by Professor Karin Schnaas, focuses on non-uniform atom distributions in compressed sensing, sparse approximation, and dictionary learning. We're excited to have him here to tell us about adapted variable density subsampling for compressed sensing. Take it away.
Thank you very much for this nice introduction and for the opportunity to hold this talk. As you already mentioned, I'm Simon, or Simon, whatever you prefer. And I'm at the Department of Mathematics. And I would say, let's start. So the title of my talk is Adapted Variable Density Subsampling for Compressed Sensing. And I hope at the end of the talk, you will all know what this rather lengthy title is supposed to mean. So before I start, I wanted to give a brief overview about my talk, about the structure of my talk. So I'm going to start with some compressed sensing basics, some motivation of our results, some brief history. Then I'm going to actually state the results, show some applications, compare them to some special cases in the literature. And at the end, I will, if there's time left, I will talk about the proof ideas. Okay, so what is compressed sensing? So usually compressed sensing is, there's some unknown vector x, some complex vector x in ck, okay, some integer, and we also have some measurement matrix A, which is in C m times k, which with m smaller than k. And we are tasked with reconstructing x from the measurements y equals a times x. So each row of A corresponds to one linear measurement, and we want to reconstruct x from y. So this is a linear system of equations with more unknowns than constraints. So in general, it's non-unique if there's a solution. So usually it is assumed that x, so the vector x is s sparse, where s is some positive integer, which means that only s, which can be much, much smaller than k, that only s elements of x are non-zero. This is what sparse means. And by introducing the sparsity, we hope to get uniqueness of the, we hope that we are able to reconstruct x from these measurements. And how are we going to go about reconstructing? Well, to try to recover x, we're going to solve the following optimization problem. We're going to try to find the x with the minimum L1 norm that satisfies our linear constraints. Here, the L1 norm is defined as usual, just the sum of the absolute values of our vector x. Why do we do that? Well, for one, the L1 norm is sparsity inducing. So by minimizing the L1 norm, we hope to find the sparsest vector x that satisfies this linear set of constraints. Why the L1 norm and not some different norm, you might ask? For example, the L0 norm, which strictly speaking is no norm. There's a whole lot of research going into that direction and comparing different optimization problems that look at how to best recover a sparse vector from such measurements. Just very briefly, the L1 norm has the big advantage that it's convex. So compared to the non-convex L0 norm, and that's one argument why the minimizing the L1 norm is basically standard in compressed sensing theory. Another whole different area of research goes into how to best solve this problem. If you think of x can be rather high dimensional. If you think of x as an image, then with 1,000 times 1,000 pixels, then the dimension of x can be rather big. And you could solve this with linear programming, some simplex algorithm, but or as I already said, the dimensions can get quite big. So what one usually does is approximate the L1 norm with something differentiable and then use some sort of approximation technique or gradient descent. But again, I'm not going to go into more detail about this, just so you know, I'm going to use some approximation of the L1 norm and then gradient descent. But that's a whole different story. Okay, so that's the basic setup of compressed sensing. Now we're basically asking ourselves, under which conditions on A can we reconstruct some sparse vector X? And you might say, well, I heard about that. If I can sample A, if A is a Gaussian matrix, then I can reconstruct it with very high probability. Well, if I give you the following task, if I want to recover the following image, like a 2D image of a brain inside your, you might again say, okay, take Gaussian measurements and then reconstruct, it should work. But you're usually limited by the hardware that you are given by some engineers or some applications. So that's why one can't just take Gaussian measurements. And the setting that we are looking at is we have some fixed measurement technique. Here in our example, I want to give you the toy example, the motivational example of saying, okay, I give you the task of recovering this image from 10% of the Fourier measurement. So if you think of the 2D Fourier matrix as each row corresponding to a tuple of frequencies, in the 2D Fourier measurement case, I will task you to reconstruct this image with only 10% of the measurements. So the natural question that arises is here, which frequencies should we take? So formally, we assume that we are given some unitary matrix A0, which represent the set of possible linear measurements. So each row of our matrix A0 corresponds to one linear measurement that we could take, but we can't take them all. So if you would have access to all measurements, then the reconstruction problem would be simple. It's just a simple inversion. But you're only allowed to pick M, for example, 10% of K measurements randomly. And how do we do that? Well, we specify a probability distribution. So we say we have M IID random variables that define, so we are allowed to pick M times, M is some integer, and our pi K right here define the probability of which frequencies in our example of the 2D Fourier measurement case, which frequencies we pick. So we are tasked with devising a optimal subsampling strategy, so finding optimal weights so as to ensure recovery with very high probability. That's the setting we're working at. And given such pi K, we define our sensing matrix. Basically, you can forget about these normalizing constants. So basically, we just put all of the measurements that we chose via our random variables. We put that into a element C M times K matrix. So we stack the measurements over each other, take the measurements, and then we try to recover our ground truth image from the resulting measurements. So it all hinges on defining this subsampling density, this subsampling strategy to ensure optimal recovery. And that's basically what we're going to try to do in this talk. To devise a strategy to ensure recovery with high probability in this setting where we're given a set of possible linear measurements and only a small budget of M frequencies or measurements that we are allowed to take. So basically the big theoretical questions in the grander scheme of things is how big does M have to be? So if I could make M as large as possible, so take as many measurements as I want, then I could take them all and just invert the matrix and would be easy. So I want M to be as small as possible. Think of a clinical setup where, for example, an MRI machine, the longer the patient has to be in there, the more expensive and the more they will move. So taking as few measurements as possible is always better. And how should we choose them? So how should we define this these subsampling probabilities pi k? So you might ask yourself, well, I showed you this nice image of a brain, but is this really sparse? Or are signals in general really sparse? And the answer is, in practice, not. But most of them, if you think of images, are sparse in some different bases. If you think of this W here as some form of wavelet basis, then it's well known that if I take an image and transform it into a wavelet basis, then it is approximately sparse. So we can assume that it's sparse in some wavelet basis. Same holds for audio signals. So most natural signals are sparse in some different bases. So instead of solving our minimization problem, our original minimization problem, we can just, if X is not directly sparse, but sparse in some different bases, we can transform our problem by introducing this new variable set, where set is such that X is W times set. So we can just take our image, transform it into a wavelet basis, and we just get a new measurement matrix AW. Instead of A, we have now this new measurement matrix, which would be in the above case, which would be Fourier and some wavelet basis, let's say the Haar wavelet basis. So this would be our new measurement matrix. And we can again assume that we want to recover a sparse signal from a set of linear measurements with this measurement matrix. So this is just going on behind the scenes, in case you were wondering, well, is this assumption of sparsity even something which makes sense? So what are, compressed sensing is nothing new. It's been around for quite some time. So what are like existing results? How should you proceed in this kind of setting? And for that, we are going to introduce some more notation. So we call I, big I, the support, basically just the set of indices such that xi is not equal to 0, with I equals to our sparsity parameter S. And very early, like 2006, 2007, the very early results showed that if you really have a sparse signal, so not sparse in some basis, but a really sparse signal, so if your measurement rate, so your set of possible linear measurements really is the discrete Fourier matrix, then you should choose uniformly at random. And by doing that, you are ensured perfect recovery with probability, with extremely high probability. But as I already mentioned, most natural signals like images, for example, a brain image that I just showed you, is not directly sparse, but sparse in the basis. So these very early results don't apply. So this is why compressed sensing theory evolved. And I'm paraphrasing here, but the next results historically said something like, well, the optimal subsampling strategy pi, so the probabilities with which we pick each measurement from our set of measurements, should depend on the structure of the matrix A0. So if our signal, so the structure of our measurement matrix should play a role into which measurements we take. This was still not able to bridge the gap between what we observe in practice. So in practice, all of this subsampling works very well, but the theory was like lacking behind the practice. So the next results, like very recently, 4 or 5 years ago, maybe, said something like this strategy. So these probabilities should not only depend on the structure of the matrix, but also on the structure of the sparse signal. So it should, if the non-zero locations are all on the top of the vector, should make a difference, or if they're at the bottom. So the subsampling strategy should take into account where the locations of the non-zero coefficients are. This has the huge drawback that you actually need information, concrete information about the locations. So about the sparse support, you need to know where the non-zero coefficients of your vector x are, which in practice might not be such a reasonable assumption. And this is exactly where my results come in. I will show how the optimal subsampling strategy, so how our probabilities of picking, so of spending our measurement budget, if you want to call it like this, I show that it should depend on the structure of the matrix, so far nothing new, and on the distribution of sparse supports. So I'm going to assume that our signals are generated by some underlying probabilistic model. And if I know how the distribution of this sparse supports are, if I know the distribution of the locations of the non-zero coefficients, I can leverage this information to again derive a density which should give better reconstruction results. Why is this different to the assumption of knowledge of the sparse support? Well, the distribution, I can estimate the distribution from data. So if you task me with sensing a brain, I can take brain images from the internet, transform them into a wavelet basis that sparsifies them, and then estimate the distribution of the sparse coefficients. So I can, in some sense, leverage the information that my data that I'm looking at lives in some subspace, and leverage this knowledge of structure, underlying structure in my data to again derive optimal subsampling strategies. So it all hinges on this distribution of our supports. So to do this, we need a formal probabilistic model on our supports. We chose the rejective sampling model, which is basically just a probability distribution on all sets I subset of 1 to k with cardinality S. So we define this via these weights omega 1 to omega k between 0 and 1, which we assume that they sum up to S. And then we say that our supports follow this distribution if this if each I gets picked with this probability right here. Well, this might look not very counterintuitive, but it actually has a reason why we chose this. So it has the advantage that we only pick supports with the size S. And on average, each omega k corresponds to the probability that a certain location is in the sparse support. So this means if, for example, k equals 1, then omega 1 corresponds to the expectation, so the probability that you would see the location, that the vector x has a non-zero coefficient in location 1. This is also very important once if we want to estimate these omega from data. So we can just take a frequentist approach, but we will later talk about this. So just so you know, we specify our distribution on the sparse supports via these omegas. So these are basically what we call weights. And we write d omega for the diagonal matrix with the weights on the diagonal. Further, we need a signal model to derive theoretical results. Now we have a probabilistic model on our supports. We also need to generate signals. Note that so we say x is just a sum of some linear combination of standard basis elements. So ei denotes the standard vector with the 1 at the ith coordinate, and ci are some fixed numbers in R, and we assume that the sign flips. So you're either -1 or +1 with equal probability. And again, the support, so the location of the non-zero coefficients follows our random support model. This is basically the generative signal model that we assume that our data that we look at is generated from to derive our theoretical results. Now, is this a realistic model? Well, you can, with the this random support model, you can basically generate any distribution that you want with a certain dependent structure. So in general, yes, it works. You can tune this very well so that it fits actual data, noiseless, but it works well enough. And now with all of this work, we are finally able to state, I'm finally able to state my main result, which is currently in preparation, but should be out hopefully very soon. So if we assume that we are given signals that follow our signal model, which we just seen with weights omega 1 to omega k, and if we assume that our measurements are sampled according to probabilities pi k, we are not specifying them yet. We just say, okay, if our measurements ak are sampled according to some pi k, then the sufficient condition that we recover our unknown vector x from measurements y equals a times x, where a is now like basically just the sampled measurements. If we sample m, so if we satisfy these conditions, so if we sample enough, depending on what this fraction right here is, then we will recover with high probability. This is basically showing how the number of measurements plays together with the sampling probabilities, with the coherence of the matrix. We call this up here the coherence of the sampling matrix. So basically just the biggest entry of each row of AK of A. The infinity norm gives you basically just the biggest entry, and we square that. That's the coherence. And here we see basically how all of these ingredients fit together. We need M. M is the budget, so the number of measurements we are allowed to take. We need that it works together with the weights via this diagonal matrix d omega, the sampling probabilities, and the structure of the matrix. So it all plays together. Now this might seem very abstract, but what this allows us to do is to say, well, I have this result. How should I choose pi k? Now, which values should I actually, if I assume that I have knowledge of the omega, so I have knowledge of the distribution of sparse supports, how should I actually pick our density, our subsampling density, such as to minimize the constraints on the right-hand side right here? This is exactly what we're going to do. So we're just going to set pi k as the maximum between these two quantities. So it's just basically setting these two values, so balancing these two constraints basically. And we're normalizing our pi k's in order to ensure that we actually have a probability distribution. And if we pick our, again, this assumes knowledge of the omega via this diagonal matrix, so it assumes knowledge of the distribution. And if we pick our frequencies or our measurements like this, we get the following lemma. Again, if our signals, the signals that we actually try to reconstruct are generated by this model that we specified above with weights omega 1 to omega k, and if our measurements A are sampled according to this probability distribution, so if these are our pi k, our strategy how to pick our measurements, then this is the sufficient condition on the, so this is a lower bound on the number m of measurements that we need to take in order to ensure recovery with high probability. So yeah, for those of you who are familiar with standard compressed sensing results, we will later come back to this and compare it to some of the existing results. But for the moment, the important thing is we now have a clear way of, if we have knowledge of the distribution, how we should choose the measurements via this relation between the structure of the matrix and the distribution of the sparse support. So this is a concrete formula. If you have knowledge of the sparse supports, then this tells you exactly how you should choose your measurements. Yeah, it's right here again. But so it depends on the distribution. And here, the important thing that I already mentioned is we can estimate this distribution very well from data. So if I have data, I can leverage this information to to generate an approximation for our underlying distribution. So how I'm going to go about that? If I have like a data set of brains, for example, then as I already said, they are not directly sparse, so I have to transform it into some form of wavelet basis. I'm going to apply a threshold to really sparsify it and just throw away the very small coefficients of these images in the wavelet basis that I chose. And then I'm just going to count how often each basis element of our wavelet basis is appearing in the sparse supports, which gives me the approximation of the inclusion probabilities omega k of our rejective sampling model. And if we again circle back to this example with the brains, I just picked a random data set from the internet, which is rather diverse. So I'm not like cheating where each image looks exactly the same, which basically amounts to having exact knowledge of the image. So our data set is rather diverse. As you can see here, it's like different locations of the brain. And if I use this training set of data and transform them into a wavelet basis and then count how often each basis element gets used, this is the heat map of the weights. So these are the estimated omegas for this training data. So what we can see here that there's a lot of underlying structure in brain data. So there are certainly some wavelet basis elements that get used far more often than others. If you look at here, I've put the weights in order, and what we can see is that there are certainly some that the signals that we want to measure live in some very structured subspace, and with this estimation of our weights omega, I can now go and plug this into a formula right here to get the following density for taking our measurements. So this is the reference image again. These are the omega that we estimated from our training data set. The resulting subsampling strategy, so the resulting subsampling density is depicted right here in a log scale. Recall, we are looking at the 2D Fourier transform. So each row corresponds to a tuple of 2 frequencies. And what this basically tells us that we should sample the center, so the low frequencies with a very high probability, and the lower frequencies with very low probability. For comparison, I've put a heuristically inspired state-of-the-art subsampling strategy next to it. So basically, this says, okay, you should your density, your subsampling density should decrease polynomially. If we then go ahead and take 10% of measurements according to our probabilities, these are the resulting locations. So basically the locations of the measurements that we want to take in the K-space, in the 2D Fourier K-space. So each white point right here corresponds to one linear measurement from our 2D Fourier matrix. And what we can see is that we outperform the heuristically inspired subsampling strategy. This doesn't come as a surprise. We assume we have far more knowledge of the data, so we know the data has some structure. And what we can see here is that our subsampling density adapts to the underlying structure of the data. Here we assume use the 2D DB4 wavelet basis as sparsifying basis of our signals. So this difference between this heuristically inspired and our adapted density gets far more pronounced if we use a non-symmetric data set. So if we look at, instead of brains, if we look at knees, for example, again, some random example, then by doing the exact same analysis, taking a data set, transforming it into the DB4 2D wavelet basis, taking a threshold, and getting an estimate for the underlying distribution, which we plotted here, we see there's more structure into this direction compared to this. Looks like more symmetrical, to the X and Y axis. Here it's more to one direction. And again, if we use these estimated omegas, these estimated weights of the underlying distribution of the sparse supports to generate our pi, we see that our optimal subsampling density adapts to the data. And we sample more into this direction than into this direction. And we are able to outperform the heuristical subsampling strategy considerably. So the more non-symmetric or non-standard your data set, the more you outperform. And we do this by leveraging this information about where, in which subspace our signals live in a probabilistic way. Well, modern compressed sensing theory, like if we go back to this example, this basically says you should take this measurement and this measurement and this. So basically just random frequencies in the 2D Fourier space. This is not practical in practice. So usually you have some underlying structure in your measurement devices or something. So what one usually does is one blocks them together. So instead of measuring each, instead of being able to access each linear measurement separately, we now look at the setting where they are comprised in blocks. So for example, each line in the 2D Fourier space might correspond to one block. So you fix one frequency and let the other one go through the K-space. So this might be one block of measurement. Now we want to derive again a probability measure, a subsampling strategy on these blocks. So each measurement now comprises of a lot of measurements which are in one block, and we want to specify which block we pick with which probability. Now we get exactly the same result, basically, with just instead of AK here, we get BK, and here it is the operator norm instead of just the absolute value. But other than that, our theory easily goes through, and we get the exact same result. And if we look at applications, so right here we see two kinds of blocks. As I already said, one very popular kind of blocks is to take lines in the vertical lines or horizontal lines in the 2D K space. And what are, if we again use our adapted subsampling strategy, we get a very nice distribution on the lines. So we should pick the lines in the middle with a much higher probability than lines that lie further away from the center in the 2D Fourier case. And the same can be done with square blocks. So instead of lines, we want to take blocks of measurements. So we bundle a few frequencies together, and now we get again, these are in log scale. So this is just the distribution. And what we see that, again, we should measure the center, and so the low frequencies should be measured with a higher probability than the high frequencies, which is quite naturally, because if you look at again at the distribution in the wavelet basis, it's again the low frequencies that are far more frequently appearing in the sparse supports of our signals than the high frequencies. So again, adapts to the structure on the underlying structure of the signals. And down here you can see the actual reconstructions. So we used these measurements to construct our measurement matrix, measured this image, and then used L1 minimization as introduced above to reconstruct. And we can see that we are able to get very nice reconstructions with 10%, I think, or 20% in this case. But in the line case, there are more artifacts. That's to be expected, because we basically have no information in the vertical K-space. Okay, so we now have seen how to apply our result, and that our result actually outperforms the state of the art by taking the structure of the data that we are looking at into account. And now we want to ask ourselves, well, how does our theory, so how do our theoretical results compare to existing results? And one of the early results basically is that this lower bound on M. So now we again turn back to comparing lower bounds on M, as we now have seen that the pi k, as we derive them, outperform. Now we want to see if our lower bounds on M are also able to keep up with existing lower bounds. So here you see that M should be of order S times the sum of the coherences times log, some log factor, and some, this is the way that they chose it back then, like 10 years ago. And to get a better feeling for this result, if we are going to look at two special cases, if A0 is the Fourier matrix, then AK, the infinity norm square, is going to be 1 over K. In this case, this sum of coherences is going to be 1. In this case, we get basically optimal reconstruction, a guarantee of order M should be of order S times log K, which is optimal. From a stability standpoint, you can't get much lower than that. If on the other hand, if we have like a very coherent, so if the coherence is very big of our matrix, if we have, for example, A0 equals the identity matrix, then each AK is just the basis vector EK, and then the sum of these coherences is going to be K. So we would have to, this lower bound then breaks down and would say, okay, you should sample multiple times the whole space in order to guarantee recovery. This is basically the reason why people started to take the structure of the signals into account. Like here, we assume no structure in the support, only that the number of S is known. And if we compare this to our result, instead of a times right here, we have a plus, which means that our results are not only able to cope with these different extremes, like very incoherent, so very small coherence matrix, or very big coherence, but it also gives us lower bounds on the number of measurements N. Now, this is not a very fair comparison, to be honest. We assume knowledge of the distribution of the sparse coefficients, so we assume more knowledge about the signals that we want to measure than the result right here. But if we compare our results to more modern results in compressed sensing theory, which are very complicated because they assume very detailed knowledge of the structure of the signals, and it gets very technical very fast, so I omitted it right here. But basically, we are able to recover those results up to a log factor perfectly. So we our lower bounds on M are better than standard results for unknown supports, and we are on par from our theoretical standpoint with recent results, assuming perfect knowledge of the sparse supports. Well, the idea of the proof is rather, it's not that hard. So basically, it follows standard compressed sensing proof ideas up until a certain point. So we have the condition, if again, I is the sparse support, if we assume a fixed support for a moment, that this condition right here tells you, if this is satisfied, then L1 minimization, if you do it perfectly, is able to recover X. So this is basically what we have to show. So the first step, okay, we assumed randomness of the signs, so we can use a Höfting's inequality and a union bound over all elements in IC, so in I complement. So this is the infinity norm, so just the biggest entry of this vector. This is a vector right here, and we are going to apply Höfting's bound to each element of these to get approximately that we need the sufficient condition of the infinity 2 norm. So basically just the biggest row norm of this matrix should be of order 1 over square root log k. If this is satisfied, then this follows by using the randomness of the signs. The next step, also quite standard in compressed sensing theory, is to hold I fixed and then look at this matrix AI minus the identity. So basically we want to ensure that the inverse right here. So by showing that this matrix right here in the operator norm concentrates around the identity, we show basically that the inverse right here doesn't explode. So that's basically what we want to bound right here. How do we do that? Well, we know that we choose the subsampling, so which measurements we take randomly, and we have these nice normalizing constants, which I told you not to worry about, but here's where they appear and where they are important. So this ensures that this matrix here, so this random matrix right here, on expectation is the identity. So by scaling our matrices B, pi r pi and m, this ensured that the expectation of AI star AI minus I equals 0. And what we then do is, okay, we write this as a sum of random matrices, independent random matrices, and use matrix Bernstein inequality to basically bound the probability that AI star AI minus I 2 is bigger than some constant. So we want this to be very small. And once we have that, we get the following sufficient condition. We need that for a fixed I, the operator norm of the submatrix is very small, is of order log 1 over log square. And this is basically where we deviate from standard compressed sensing theory. This is where our magic ingredient comes in, where we use the randomness of our supports, this additional knowledge of our supports to bound this with high probability. How do we do that? Well, we use a result that we showed 2 years ago. I showed this with my supervisor, Karin Schnass, where we basically showed that if we have a complex matrix with a 0 diagonal and assume that the support is again chosen according to this rejective sampling model. So this is where it again comes in with our weights omega 1 to omega k. If these three conditions are satisfied, so this is basically the biggest entry of H. This is some weighted L2 norm in some sense. So recall that d omega is just a diagonal matrix with the weights on the diagonal. So you basically multiply each column of our matrix H with the square root of the corresponding weight, and you want the biggest row norm of this matrix to be small. And if these three conditions are satisfied, then the operator norm of this matrix, of the submatrix HII, so basically you have the big matrix with 0 diagonal H, and HII just means you pick the columns and rows indexed by I. I could be, for example, 3, 5, 7 or something like this. So I is chosen randomly. So this is a random submatrix of the big matrix. So that's why the paper is called submatrices with non-uniformly selected random supports. So by picking randomly a submatrix of this bigger matrix H according to our rejective sampling model, we get sufficient conditions, and if they are satisfied, we are able to bound the operator norm, so the largest singular value of the submatrix HII with high probability. And once you have that, by applying this theorem to to this matrix right here, we basically finished the proof. So this is the last step. We just now, instead of holding I fixed, we now use the knowledge that I is generated by this distribution model, and are able to use this last concentration inequality to bound the probability that this is actually we bound the probability that this is bigger than this. And with that, we are basically done with the proof. So to sum up, I showed that the subsampling density, so the strategy of how to spend your budget, if you want to call it that way, should depend on the structure of the sensing matrix and on the distribution of sparse supports via these weights omega-1 to omega-k. This has the big advantage that it's easy to estimate from data. So if you have a data set of similar data, you can just estimate these weights, plug it into our formula, and there you go. And this leads to state-of-the-art performance. For basically, you can choose any matrix. I only showed you examples for the 2D Fourier matrix as measurement matrix and some wavelet basis, but it basically works for every unitary matrix. So it's not limited to these special cases. I just used them for illustrative purposes. And yeah, and it also works for blocks of measurements, which is highly relevant for practical applications. So, and with that, I'm finished, and I want to thank you very much for your attention. It's like perfect timing. And here are a few of here's a little bit of the literature that I used. These are quite standard works in compressed sensing. And well, yeah, here's the last one. So quite a few, but yeah. So thank you very much. And if you have any questions, feel free to ask me.
All right. Thank you, Simone. Let's all hit that reaction button. Show our appreciation for that talk. Sorry, smash it, because you have to smash the button. And if there are any questions out there, we can stop the recording